two functions are inverses if they undo each other. So the topic of this section, 3.7, 3.8, is how to use what we know about inverse functions to find derivatives of an inverse function when we know the derivative of the original function. So just things to remember about inverses. Inverse functions undo each other, and if one function, the domains and ranges for inverse functions swap. So if one function f contains the point a comma b, then f's inverse, which we call f inverse, and you can see this notation we use for it, f inverse of x, contains the point b comma a. So probably you can already imagine that x squared and square root of x are inverse functions because squaring and square rooting undo each other. So we're going to see what that means to us about derivatives, remembering the derivative means slope. So here we're just going to focus on those blue parts for now. I have the function y equals x squared, has a shape like a parabola. I know it contains the point 2 comma 4 because I can use the x coordinate 2. I can replace this x with 2 and find my output is 4. So there's a point on the graph of y equals x squared, which is 2 comma 4. I can find the inverse function, which we can think of as, we can prove is the square root of x. And the square root of x has what we call a corresponding point. So if 2 comma 4 was a point on x squared, then 4 comma 2 is going to be a point on the graph of square root of x. And that would be right here. So check out what we can notice about the slopes. So here we go. So I can take the derivative of both of those functions, and the derivative of square root of x is 1 over 2 times the square root of x. I could find the slope at both of those points, those corresponding points. So there's a lot of stuff here. But it pretty much just says that the derivative of f is 2x, and the derivative of f at the place where x equals 2 is 4. That means the slope of the graph of y equals x squared is 4. And that's what this red tangent line is. That tangent line has a slope of 4. I can compute the derivative of square root of x. And I can evaluate it at that corresponding point. That's square root of, at the place where x is 4 and y is 2. You can see that work down here. And it turns out the slope is 1/4. So we can use lots of cool math to figure it out, but this is the big idea here. The derivative, the slopes of inverse functions are reciprocals at their corresponding points. So you're going to see it with all the missing pieces of your picture filled in. At the point 2 comma 4, the slope of one graph, f, is 4. That means at the corresponding point, 4 comma 2, on the inverse of f, the slope is going to be 1/4. There's going to be reciprocals. Notice a common error here is to assume I mean opposite reciprocal, like they were perpendicular. I'm not guaranteeing they're perpendicular. I'm just saying that their slopes are reciprocal, so 1/. Same sign, but the fraction is flipped over. So this is one way to summarize that relationship. So feel free to write this down. And you could use these words. The derivative of f inverse at f of a is the same as the reciprocal of the derivative of f evaluated at a. So this is, again, this notation. I want to do some examples to show you how it's going to come up on the AP test and what techniques you might use to answer a question that requires this knowledge. So let's make sure you've got this filled in. If a function f contains the point a comma b and has a slope of m at that point, its inverse function we will call f inverse of x. That looks like a -1 exponent, but it's not an exponent. This is part of function notation. This means the inverse function of f contains the point, remember, domains and ranges switch, so that's going to contain b comma a, and has a slope of 1/m, the reciprocal of m. So this next example is how you're going to see it on the AP test. If f is a function, and I know that f of 3 is 15, and f of 6 is 3, there's extra information here just to try to throw you off. And I know f prime of 3, which is the slope of f at the place where x equals 3. And I know f prime of 6 is negative 2. And I know now that g and f are inverses. That's what this line means. G of x is f inverse of x. Can I find g prime of 3? So we're going to use this information that's in the box, sort of a summary of what we saw in this graph from above. And we're going to try to answer this question, what is g prime of 3? So I'm going to show you how I like to answer this question. I like to make the two little double T charts that you're looking at. And I know some information about f, and I know some information about g. So I'm just going to label, and one of these charts is going to be for f, one is going to be for g. And the thing that I've been asked to find is the slope of the g function, g, at the place where x equals 3. So the only thing I know so far about the answer I'm looking for is that it comes from making 3 the input to the g prime function. Well, I don't know hardly anything about g or g prime. So how am I supposed to figure out the slope of g prime at the place where x equals 3? I'm going to use all this information, like every single thing that showed up in that box we're going to need. So I'm going to need to know something about g prime. I'm going to need to know something about the y coordinate here, because all of the information I have, all the information I've been given is about the f function and f prime. And I'm supposed to answer a question about g. So I'm going to need to fill in all 6 of these places to be finished. So the first thing I notice is that if I want to find out g prime of 3, then the corresponding point on the f function, if 3 comma something is on the g function, then it must have been something comma 3 on the f function. So the first thing I notice is that whatever the x is for the g function that I care about, it's going to be the y of the f function. So now I can fill in that x. What is the input to the f function that makes the output 3? Well, that's this one. F of 6 is 3. So at the point 6 comma 3 on the f function, something's going to happen. The corresponding point is going to be 3 comma 6 on the g function. So the thing I'm missing, what's the slope of the f function at 6 comma 3? Well, that's going to be f prime of 6, which is negative 2. And if the slope of f at x equals 6 is negative 2, how do I find the slope of g, the inverse of f, at x equals 3? Well, that's going to be the reciprocal of the slope. These are corresponding points, 6 comma 3 on the f function and 3 comma 6 on the g function, 1 over negative 2. That's 1 divided by negative 2, or negative 1/2. So these are the derivatives of these 6 inverse trigonometric functions. You notice the way this chart is organized? We have rows that contain what we call co-functions. Sine and cosine are co-functions because one has a co in front of it. And then tangent and cotangent are co-functions. Secant and cosecant are co-functions. And just notice, if it helps you, if you were trying to memorize these rules, which you have to do, here's the derivative for the inverse sine function is exactly the same as the inverse for the cosine function, except there's an extra negative. So the co-functions have a negative, where the not co-functions don't. So derivatives of inverse co-functions are opposite. So I will publish a separate video, which is optional, to tell you why on earth the derivative of inverse sine of x is 1 over square root of 1 minus x squared. Not required, but it is required that you know these formulas because we're going to use them in class and on the AP test. And then the other thing to notice about this chart is this is the first time we learned a new derivative rule since we learned about the chain rule. So now that we know about the chain rule, instead of just telling you how to take the derivative of inverse sine of x, I'm going to give you This is a formula we can use to take the derivative of inverse sine of some function of x, and this incorporates the chain rule. All right, so these get copied onto your notes, and they get memorized. Sorry, Chapter 3 is a lot about memorizing. Chapter 4, we're going to use all this stuff that we learned in Chapter 3. All right, so this first example here, I need the derivative with respect to x of inverse sine of x squared. So we might like to know that in this case, u equals x squared. It's like the inside function, right? So we could have done this with composite function notation, or we're going to do it like here because we're going to practice using that chain rule version of your rule that you just wrote down. So how do I find the derivative with respect to x of inverse sine of u? That's going to be dy dx equals, and that's going to be 1 over the square root of 1 minus u is x squared, but u is supposed to get squared, times the derivative with respect to x of u, which is, in this case, the derivative with respect to x is 2x. So that's a great answer. Feel free to not simplify it on the free response section. Just notice here, I'm going to come up and simplify this just a little bit. The most common error I would expect to see is failure to square that, or to know that you're supposed to square it but incorrectly square it. So what is x squared squared? That's x to the fourth. So if I wanted to simplify this, this could be also that 2x could come to the top. Square root of 1 minus x squared squared is x to the fourth. That's the derivative of the inverse of sine, the inverse sine of x squared. And then one more example here. Oh, 2 more examples. I'll do another video.